Lesson 6.1, Riemann Sums. We're going to find the area under a curve in calculus. What happens is you're given the function f of x, and Riemann came up with this process to find the area under any function between the x-axis and a given interval. Usually the notation is from A to B, A representing where you start collecting area, B is where you end collecting area. In this example, we're going from 0 to 6, and we're going to find the area under the curve from 0 to 6. You have to be given the number of subintervals, which means how many rectangles, because to find the area, we're going to approximate it using rectangles because that's the easiest shape from geometry to use to get area. We're going to start with dividing our base length total of 6 units into 3 subintervals. So 6 divided by 3 would give me a width of each rectangle of 2. Go down, 0 to 2 is the first rectangle. If I'm doing a left sum, that means the left side of the base determines the height of the rectangle. I go up until I hit the curve. I hit about 3. I go across and back down. That's my first rectangle to approximate the area under the curve. You can see there's a lot of area above the curve. That is okay, because again, this is an approximation and it's a gross over approximation because the base of my rectangle is so big. Once we refine the rectangles and go smaller and smaller, the approximations become better. Next, I'm going to go from 2 until 4, because again, it's a base length of 2. And there's my base right here. I'm going to go up at the left end point of the base because I'm doing a left sum. I'm going to go up until I hit the curve. It's looking at about 1. I go across and down. This one is an under approximation. We're at an under approximation because we're changing over from a decreasing function to an increasing function. When we're decreasing, coming from the left side, it's an over approximation. When it's increasing, it's going to be an under approximation. The last interval goes from 4 to 6. So there's my base length of 2 units. I'm going to go up on the left-hand side. At 4, I'm hitting the curve again at about 3. I drop down, and there is my third rectangle to approximate this area. What I do next is I say area equals, just like with rectangles, you do a base length of 2 times the heights. I have 3 different heights, and what happens is in my example, they're pretty easy heights to get, but they won't all be easy heights. We're going to use our graphing calculator to get those heights. We're going to use the stat feature on the calculator. So you hit stat, hit enter to get to the edit part of stat, and you'll see some lists. I already have information in there, so I'm going to go up on top, put my cursor on L2, hit clear, enter. Gives me a clear list. Go left, up, I'm on L1, hit clear, enter. Do not hit delete, it gets rid of the list. I have blank list 1 and list 2. In list 1, we're going to put the x values where I would like to get the corresponding height of my function. In our case, it was 0, enter, 2, enter, 4, enter. Those were the heights that we collected, or those are the x values where we collect the heights. I'm going to go right to list 2. In order to get the heights, I have to take and move up so my cursor is on L2. I have to give it a formula. But when I'm working in the statistical mode, I have to reference it back to my x value, but my x value is now in list 1. So L1 becomes the x. L1 is located above the number 1. So I'm going to put my formula in, but instead of x, I'm going to use L1. 0.5 second number 1 for L1 squared minus 2 second L1 plus 3. Then when I hit enter, I see the 3 heights, which makes sense because that's the 3 heights that we got on the graph, which are 3, 1, and 3. So I'm going to take a moment, write those down. 3, 1, and 3. My total area should be 7 for all the heights times a 2 for the width, should be an area of 14. However, they're not all going to be this easy, so I'm going to show you how to use the calculator to get that final area. Hit second quit to get back to the home screen. You want to total up the values in list 2, so I can simply double it, multiplying by the base length in this case. I'm going to hit second stat. I'm going to go over to math, and I want to do option number 5. That will sum my list 2. List 2 is above number 2. Second L2, close the parenthesis, I sum it, I get 7, which is what we thought. Then you can just multiply by the width of whatever your base is. In this case, our base was 2. And we get the total area approximation of 14. That completes the left sum. Next, we're going to do a right sum to show you how a right sum works. For a right sum, we're going to do this one with 6 subintervals, a little bit different perspective. So I still have total distance across the x-axis of 6, but I'm breaking it into 6 rectangles now. So that means each base length will be a base length of 1. I'm going to start at 0, go 0 to 1, so it's a smaller base. I'm going to go up now on the right-hand side. So I'm at the number 1 on the x-axis. I go up, hit the curve, and I backtrack across. So my first approximation is an underestimate. Now notice it's still a decreasing function, but I'm going reverse direction. So I have less area, but it's still an approximation. I'm going to the next base, going from 1 to 2. Again, I'm going to go up on the right-hand side, hit the curve, which is at a height of 1, and go across. I'm going backwards now because I'm going from the right-hand side. There's my second rectangle. My third rectangle goes from 2 to 3. I go from 3 up until I hit the curve. I go across, backtracking, and down, a little extra area. And so on. 4 next. So I'm going to go to 4, up until I hit the curve, across, and down. Notice it changes over as I'm increasing. I am getting extra area. I'm above the curve. I'm at 5 now, going up, and then across, backtracking, extra area above the curve. And then the last and final rectangle is at 6. I go up, hit the curve, and backtrack. There's my 6 rectangles. Area in this case is going to be 1, because each rectangle's base was 1 unit long, times the corresponding heights at the values on the right-hand side, which were 1, 2, 3, all the way up to 6. So this time we started at 1 and ended at 6. You grab your calculator, you go to Stat, and then you go to Edit, and these lists are not valid anymore. You cannot save the formula. It doesn't work like a computer. You have to clear it. It will not regenerate the correct values once you change list 1. So you clear out list 2, go to list 1, clear, enter, and you start again. I have 1, 2, 3, 4, 5, 6. So I have 6 entries for 6 rectangles. I go to the right, I go up, and yes, you have to type in your formula again. 0.5 second number 1 to get the L1 squared minus 2 second L1 plus 3. Once I hit enter, I have my 6 heights. So I'm going to take a moment and write down those 6 heights. 1.5, 1, 1.5, 3, 5.5, and 9. Those are my 6 heights. Again, to total, second, quit, you're in your home screen. To get that summing feature, second, stat, over to math, sum, and I'm summing list 2, second, number 2, enter. I'm getting 21.5 for my total. Don't have to multiply that by 1, I already know the answer. I get 21.5 for the approximate area on the right-hand side. So that would be a Riemann right sum. The next technique is a midpoint sum. For a midpoint sum, you're going to go to the middle of the base to create the height of the rectangle. So for a midpoint sum, we look first how many subintervals. I have 3. So I'm going to take again that 6 units divided by 3 back to a base length of 2. I start here, I go 0 to 2, but I want to go up in the middle because I'm doing a midpoint sum. So I'm here at 1. I trace up until I'm intersecting with the curve wherever the height is at 1. That's the height I'm using to get my rectangle. So at that height at 1, I go to the right until I'm lined up at 2. I go to the left until I'm lined up at 0. I drop down, create my rectangle. First rectangle for a midpoint sum. Rectangle number 2, base length. I'm going from 0 to 4. Again, I'm going from the midpoint. I'm going at 3. So I go up, figure out where the curve is intersecting at 3. That's the height. I go across, across. That's rectangle number 2. Rectangle number 3, from 4 until 6. I'm going from the midpoint. That would be at 5. I go up, figure out where 5 is for the curve, find that point. I go to the right until I'm lined up at 6, left until I'm lined up at the 4, and I drop down on both sides. Here's rectangle number 3. This one's area approximation is going to be base length of 2 times the heights at the midpoints. The midpoint values were at 1, 3, and 5. Back to the calculator. Stat, edit, up to L2, clear, enter. Up and over to L1, clear, enter. I have my clear list. I input the X values to determine the heights, which were 1, 3, and 5 for this midpoint sum. Right arrow and then go up. Make sure the cursor again is on L2. 0.5 X, oops, mistake there. 0.5 second number 1 to get L1, not X, squared, minus 2 second L1 plus 3. Hit enter, and I get the 3 heights. Your heights is a double checking feature. Here should be matching what you're seeing graphically as you go through and do a Riemann sum. I'm getting 1.5, 1.5, and 5.5. 1.5, 1.5, 5.5. So the area total, go to the home screen, second, quit. I want to sum the heights. Second, stat, right arrow to math, sum, I want to sum list 2. Second, number 2, hit enter. I'm getting a total of 8.5. And then times 2 for the base length to get an area of 17. So the approximation using a midpoint sum with 3 subintervals is giving me an area of 17. Well, what Riemann came up with a long time ago was, how do I get the most accurate and then eventually the exact area under the curve? So now we're going to proceed to getting the exact area under the curve. And the idea is, if I shrink the base length so infinitely small that my rectangles are like this, they're so infinitely small, what happens is that you don't have any over or under. They're infinitely small. As we look at this, infinitely small, infinitely small. So if you can make these so infinitely small, then they're touching the graph with that infinitely small base, then I could get the area exactly. So we are summing infinite rectangles. In calculus, we call that an integral. This is the notation for an integral, summing infinite rectangles. We have to say, where am I starting to collect the integral, the area, which is summing of infinite rectangles. So I'm going to say I'm starting in this particular case at 0. So we call this the lower limit or lower bound. And then up here is the upper limit or upper bound, and in our case it's 6 because that's where we're ending the collection of area. In here is the representation of the heights and the widths of the rectangle. The height in our particular case was 1/2 x squared minus 2x plus 3. That represented the height of each and every rectangle. The width was changing along here, along the x-axis. So what we want to do is get it so infinitely small. So we're going to say it's delta x. Delta stands for change. It's changing, so it's getting so infinitely small that we're getting the exact area as we progress. The calculator will find that exact area. You go to y equals, and you type in your function as you normally would type in a function in y1. So I have my function 0.5x squared minus 2x plus 3 in my y1. I hit zoom 6 to have it graph my function. So now it's matching the picture that you can see on the paper and online. There's a feature on the calculator. Eventually we will learn techniques to integrate this, but for right now we're just doing it with technology. Above the trace key, the calculate menu is where we want to go. Second, and then trace. That gets you to the calculate menu. Option number 7 has a setup similar to my setup. That's an integral, and there's f of x, our function, dx. So I'm going to hit 7. What it does is it brings me back to the graphing screen. It's asking me for the lower limit. I'm going to tell it 0, and then I'm going to hit enter because I want to start at 0. Then it asks for the upper limit. I'm going to type 6, enter, and voila, look at that. It fills it in, and it gets me an area exactly. It's actually doing an approximation, but we can get into that when we get back to school. It's giving me 18 for the area under the curve. So the answer for this area for the integral is 18. And that's it for today's lesson.